All right. Well, let's go ahead and get started. Thanks so much to everyone for joining us for our monthly public webinar. I'm Jeremy Gregory. I'm the Executive Director of the Concrete Sustainability Hub at MIT, and we use these webinars to share some of the work that we're doing on a variety of different topics. Today, we're fortunate to have Professor Franz Ulm. He's the Faculty Director of the Concrete Sustainability Hub, and he's going to be presenting a couple different topics of different research we have related to resilience. And with that, I'm going to turn it over to Franz. Take it away. Oh, sorry, one last comment I wanted to make. We have everyone muted because just to try to minimize background noise, but if you have questions, please, there's a Q&A box that should be in the lower right of your screen. You can just type it in there and we'll receive them. And then when we have an opportunity for discussion, I'll be able to share those with Franz, and that will help us facilitate our discussion. So we really want to hear from you. So type those questions in the Q&A box. Take it away, Franz.
Thank you very much, Jeremy, and good morning, everyone. Thank you for taking time out of your busy schedule to hear something about resilience today, about the work which we have been doing in the Hub, about the urban and building resilience. To start with, we have seen it all coming over and over again. Hurricane Maria, September 2017, Category 5 hurricane. Puerto Rico has still not recovered from it. You see here a map of damage that occurred in San Juan. The local damage also here. Still, Puerto Rico has not recovered. You have all seen and heard the story of Hurricane Michael, devastating Mexico Beach, Florida, hurricane Category 4, wind speeds 130 to 150 miles per hour, as predicted by current code maps, and still, despite that fact, 54% of all the buildings have been destroyed, 23% severely damaged, except for one building, as you see here, which apparently had not much damage. Impact of hurricane damage, wind and floods are huge. Hurricane Harvey alone, the estimated cost was $150 billion, second only to Hurricane Katrina. The top vulnerable states or states areas is New York, the first place, $292 trillion, Florida, Texas, Massachusetts, where I'm talking from, and New Jersey. If we just take from 2017, the cumulative cost of the 16 separate billion-dollar weather events in 2017, it was $306.2 billion. I mean, these are numbers which are unimaginable and cost enormous money to all of us. So, will this get any way better? Well, the future hurricane damage is expected to increase because of warmer climate, particularly the strong hurricanes, Category 4 and 5. Maybe the wind maps will need to be adapted for it, but it is clear that we need to do something now in order to address this issue. And have we not seen enough so far to realize that we need to do something? And let me be clear about one thing from the onset. This is not about whether you believe in climate change or not. It's not a matter of belief. This is about whether you do something now or not. And that is a key point, I think, which I would like to make. This is not about believing in climate change. This is about doing something. The second one is more professional. I'm a structural engineer by training. Realizing that classical engineering approaches somehow fail to predict their damage, despite the fact that we have the right speed maps, hurricane speed maps, for which buildings should be designed. So my conjecture here is that classical engineering approaches, which are based on what's called mean field theories, from city scale to structural resilience scale, fail to capture the key nature of hazard events. And I will dive into this a little bit more during the next 45 minutes. By mean field theories, I mean just looking at cities from a building density point of view, count the number of buildings divided by the area, so it's just a mean field approach to it. In the same way in structural engineering, where we consider continuum theories, beam theories, somewhat, if our tools were upped, we wouldn't see this enormous damage. And my point which I want to make is actually that it all comes down to capturing something which you will hear over and over from me again, is capturing fluctuations. That fluctuations are actually the key to urban resilience design. In fact, we make use of these fluctuations in our daily measurements of temperature. In fact, there's a famous fluctuation dissipation theorem in physics, which actually says that there's no dissipation without fluctuations. Now, what is dissipation? Dissipation is the energy that is released when something breaks. So there is no damage without fluctuations. So the question which I want to address throughout this talk is, what are the tools which we need in order to bring those fluctuations into the realm of engineering to address urban resilience? I will start briefly out with a background. What is actually resilience and why design codes don't cover resilience currently, at least in terms of impact. I then start at the city scale and look at the impact of city texture before going to the building scale and talking about mobility curves, fragility curves, which are used in order to define, assess, and eventually improve resilience of building stock in communities. So what is resilience? Well, resilience is very often misunderstood as a robustness. A structure which is sufficiently robust should withstand whatever type of storm that comes in its way. That may be true, but it is that's not what resilience is about. Resilience actually is shown here on the left side of the slides in this figure here. For a system is given a certain functionality. At an extreme event, there's a drop of functionality and then a recovery time. So resilience actually is the combination of robustness, so the drop. If the drop is completely, if the structure is completely destroyed, of course, you have a rebuilding here that needs to take place. But what it really makes a community resilient is the rapidity of bringing a system after such an event back to its initial performance. And this involves, in the context of urban resilience, it involves a multi-scale approach. We need to look at the loads at the city scale. And here I'm going to address the role of city texture on building pressure particularly. We need to consider the fragility curves for different building types and loads. So going beyond what is currently actually in the books already in design codes or in other type of approaches, and highlight actually value of materials like concrete or other strong materials that are able to contribute to resilience. Finally, resilience in the end needs to be brought in the context of what is the return of investment, by which I mean we need to bring together the failure at a certain time together with the recovery time, which relates to the bill of activity in order to bring a system back to its initial performance. So be quantitative from a life cycle cost analysis point of view. In fact, I won't show many equations, and don't be scared about this triple convolution integral here. All what it tells us is that are the key players that make a community resilient or not, so from an assessment point of view. There's on the one side the hazard itself. The hazard has a certain uncertainty. How often does it occur? What is the likelihood of it to occur? And that is an important issue. But actually one aspect which has been always forgotten in this here is that this is also city texture dependent, and I'm going to show you this here in a little while. The second one is once we have a given hazard, there is a certain uncertainty, probability actually, of the response of a structure. How will a structure respond to it? not on average actually, but actually when something breaks, it relates to fluctuations, because structures are designed on average to withstand something. So it's a structural response. And finally, it is the uncertainty or the probability related to the loss given this response, which is material dependent. So those three parts here need to be addressed and motivates actually this multi-scale approach, which I would like to show you. So my first point I want to make is the impact of city texture on resilience. And the key message I want to take away here is that urban geometry magnify or reduce wind loads. So city texture densities actually are already well known that they impact the pressure loads. If you look at the different categories of hurricanes that may occur, if you had just a single building here, then we could design all buildings just as if they were standing all alone all along the way. However, there are interactions between buildings and magnifications of speeds and thus pressure due to city texture that occurs. And to illustrate this here, if you see here particularly is as you go to higher wind speeds here, urban geometry actually here comes into play. Now, what is the link actually between the pressure for which we design a building, wind loads, right, and the speed, the wind speed map which are well established and actually are quite accurate in terms of occurrence here. What's the link in between? Well, we have the wind speed here from a map which is in design codes or design guidelines here. We have a density here of the air, and then we have this famous drag coefficient CD here for buildings and building types. There's also surface exposure coefficient, whether you're on the front, on the back, etc. But in fact, what engineering use in design is not directly the wind speed actually, but the pressure in order to design a structure for a certain load induced by some wind. So given the observable damage each hurricane season, what's wrong then in our approach that we are not able to capture these extreme pressures which lead to this strong destruction which we see every hurricane season, etc. So is it the maximum wind speed? Well, if you survey actually the wind speeds of the different hurricanes, they are well in the range of values which are predicted for a long time. So the wind speeds per se are not the cause that we have a wrong estimate actually of the pressures which are there. So what it comes down to is then this multiplication factor, this drag coefficient, which amplifies the wind speed here to the power 2 here, to in translating it into a pressure for which a building is designed. So what does it mean, this drag coefficient? And allow me here to make a simple thought model using kinetic theory of gases. You may remember that equation, actually, the first one here, from your high school classes. One of the most famous one of kinetic theory of gases. Basically, you have a box of a volume V. There's a link between a pressure, the temperature, and what is called the kinetic energy. In fact, if you know the temperature, you know the volume, you know the number of particles here through a number here, you know what the pressure is. So that's classical kinetic theory of gases. However, if you then write this pressure here and apply it for our situation, you actually find that the pressure here relates here to the mean square speed, which means it is the product of the velocity with the velocity. So for those of you who remember that from the introductory classes to statistics, that's basically a quantity which expresses fluctuation. It's mean squared speed, it expresses fluctuations. In fact, if we were to take away the mean value, we would, to the power 2, we would have the definition of variance, so the standard deviation to the power 2. If we take in addition then here this classical fluid mechanics definition, then you actually realize that this drag coefficient is actually multiplied by a factor here, nothing else but an expression of fluctuations over the square mean speed, with fluctuations expressing the variability of the speed related to texture. So even for gases, even if I'm not talking about any city, a drag coefficient carries all the information about local velocity distributions compared to the mean speed. Mean speed here in our application is the speed defining the design from the maps in design codes. So let me show you this as a concrete application here. This is October 10th. Hurricane Michael makes landfall in Florida. It was a Category 4 hurricane, speed 130, 156 miles per hour. Exactly that, actually, what we saw on the television screens, what was predicted. So it is not the velocity which is wrong. However, we have a pressure load here, which relates here to this drag coefficient. And, well, the velocity here of the hurricane that comes in here. So let's make a simulation, a real city model for wind simulations of Mexico Beach, simulating 1,100 buildings here by means of computational fluid dynamics, imposing from the seaside a Category 4 hurricane in terms of speed. And I kindly ask you, let's say, to just look here at this map. This is the velocity map of result of these simulations. You see from the sea a Category 4 hurricane, so a speed typically, as we said, in the 130 miles per hour range. And then you see in between the buildings, which are in blue, you see this magnification of the speed due to these urban canyons of the system. So if we just were to take for each building the pressure as a constant, the pressure, the drag coefficient as a constant, we would not capture actually with it these magnifications of pressures that results from the urban texture, from the texture here of the buildings, the way how buildings are ordered. In fact, if one looks at the damage map of Mexico Beach, which was found, which, as I said, was 54% of buildings destroyed, 23 severely damaged, except for one building here, which I showed you in the beginning. This is from the New York Times. And overlay this year with the determined with the drag coefficient, which we can determine from the simulation, we actually realize then here that the current practice actually here is such that 73% of buildings would not be covered by, in terms of pressure, by the current design codes, meaning the pressure to which those buildings were subjected is higher than the design pressure as it is currently in application. In fact, the way of displaying this here is to look at the cumulative distribution function of the drag coefficient here, where you see, in essence, here's the drag coefficient for which the buildings are designed, and all this part up here, the buildings which have been subject, because of the texture, to a higher pressure than the pressure, the design pressure for which the building were designed, and that is critical. In other words, there is a distribution of drag coefficient to which buildings are designed, which is currently not part of the practice of designing buildings in communities. So firstly, city texture matters for urban resilience, and current design codes underestimate this amplifying effect of city texture on building design pressure. meaning this is not a matter of changing the wind speeds maps. I think they are well established and they have been well studied before. What really matters here, as far as as urban resilience is concerned, is to consider and incorporate in the design the city texture drag coefficient into local design codes. This depends on the type of city. This depends on the way how we build our cities. In fact, one can generalize this approach, since I guess not everybody would like to or has the means of calculating for your city running these computational fluid dynamics calculations. In fact, that's the reason why we have developed a city texture methodology, which consists actually of enriching the description of the geometric representation of the city. A city is not just the building density, but in fact the way how we build entails a variation from that mean building density, which is expressed here by this function g of r, called the pair distribution function. It is the variation of the local density of buildings with regard to the average density of the city. In fact, the way how to obtain this is pretty much straightforward. We take data which are publicly available in open street maps of a city's building stock, extract the buildings, atomize each of those buildings into like as if it was a molecular structure, so like atoms, and then around each building we make these circles in order to determine how many buildings do I find in my neighborhood. And by doing so, one actually can find out whether a city is crystalline, or whether a city looks more like a liquid. So, for instance, if you take Paris, it's almost a gas, actually. Seattle is liquidish, and Chicago is a very clear crystal structure, basically meaning have a repetitive motif here of the system. So rather than speaking only about the average density, we enrich the geometric description and see how much that geometric description affects the here in this example of hurricanes, the drag coefficient. So the question really which we address here is how much geometric city information is needed to capture a city's response to a specific hazard. Talked about Paris. See San Francisco here, and an interesting feature actually is if you look sort of at quite a lot of numbers, you see that you have here a gaseous type city, Jerusalem, Mexico City. You have liquid type cities where Boston is part of it, and then you're moving towards crystal type structures here, type cities. Now, this all comes with what is called another parameter, which is the order parameter, which basically is if you have four neighbors, and those four neighbors are exactly spaced by the same angle around you, so basically on a square, then this order parameter would be 1. And it would decrease from order 1 to smaller values greater than 0 as we introduce disorder in the system. And there seems to be something built into the structure of cities where this order parameter, this angular distortion actually here, relates to the coordination number. What is the coordination number? It's nothing else but the average number of neighbors which each building have. So these two parameters actually suffice to describe, to add to the normal density, building density quantity in order to enrich the geometric description of a city. In fact, let me show you an example. This is from Hurricane Irma. There was a category 3 hurricane. Wind speeds were well predicted, but two areas were subject to completely different level of damage, despite the fact that they were subject to the same velocity range, same speed of the hurricane. Lee County exhibit extensive damage, while Sarasota County had minimal damage. So why is that? Why was that due? So what we did then basically is we determined this pair distribution function by basically looking first at Lee County, where you see here this highly ordered structure. You see a very pronounced crystal structure here with clear peaks in this pair distribution function, and compared it with Sarasota County, which you even see on a map higher disorder here, which is much more liquidish than the ordered Lee County city. So now, how does that affect the drag coefficient? Well, we run then simulations on the city and basically find out that this the drag coefficient, and this is just the average drag coefficient here, increases because of the order of the crystalline order of Lee County. So here, just an example that the damage actually which a community occurs is due to the texture, the way how our city is built. Well, currently we have been extending that approach, looking at not only case studies, but running more simulations in order to find out how could we possibly integrate this here for all cities worldwide. And what turns out is that the drag coefficient actually could be monitored in terms of two parameters which come from the city texture analysis. One is the coordination number, CN, so the one which we determine from the pair distribution function. The other one is this order parameter, which is an exponent here to the ratio between the wall surface of a specific building and the area of the building. So area of the building here of the footprint it has on the system. In other words, if we have this quantity determined for CN and phi for a specific city here, we can then scale the drag coefficient of a specific building actually with regard to the wall surface and the area of the building, integrate this here into the cumulative distribution function here of the drag coefficient, and add this here into the assessment of the occurrence of the uncertainty of the occurrence of a hazard. Let me now bring this from the city scale to the next scale, which is the building scale. Given that the pressures are now known, how do we know which elements break? Is it windows, roof, structural versus non-structural elements? And let me introduce to you fragility curves along that route. The approach which we're using here is molecular, inspired by molecular dynamics or molecular simulations, and I hope I will be able to show you why. So first of all, why are we doing that here? Design codes focus on robustness of structural elements, and that's absolutely critical to make sure that people escape their buildings unharmed. But they do not focus on non-structural elements. So you have here this damage in a building in Puerto Rico where you clearly see the structure is still intact, but the windows are gone, so this becomes a non-habitable space, which means it will take time for the community to recover until the windows are repaired, the non-structural elements, etc. So in the context of resilience, being defined as the time it takes to bring a system after an extreme event that leads to a drop of performance back to its initial or higher performance, the consideration of these non-structural elements are critical and not covered currently by design codes sufficiently in order to ensure resilience of our communities. So the way how we do this here is the following. We basically take a structure, discretize it by mass points, and describe the interactions in between. In fact, if this was a classical beam, then the energy here in between those mass points is simply given by beam theory. But beyond beam theory, what that also allows us to model is to model the breakage of those different bonds. And by doing so, we directly obtain access to the broken elements and thus to the necessary work required to bring the system back to performance. In that approach, we can consider wall elements, beam elements, windows, you name it, whatever we can describe in terms of interactions, energy interactions between mass points. So just to show you that this is not that we validated this approach, so what you see here is a test actually, which is quite interesting insofar as it's a buckling test actually on two different materials. One is wood, the other one is pasta. So what happens in these tests is that there is a mass hitting on from the left the system. You see the system buckles here, and below you see the simulations result, which actually correspond very well to the experimental observation, so a validated technique here. When it buckles here, it's dynamic buckling. It's quite a complicated test. You see the vertical displacement here over the beam length for a given time window. We are pretty good in predicting, actually, with this type of technique, the experimental observation. Well, not only can we model things like buckling here, but we also can model actually systems here when they fail. So you see the mass coming and the pasta breaks. Well, similar type of things we can do by simulations here. It's just not at the same magnification level, but you see the same type of damage here. In fact, if you look at the vertical displacement over the beam length, we capture here the simulations capture the experimental observations very well. In other words, this type of approach, which goes beyond the continuum theory, which are not able to capture this breakage of the bonds, this molecular-inspired approach can capture it, and by doing so, it can be quantitative in terms of the elements that break in a system. It's, of course, not only for pasta here. You see here two structures here, one made of reinforced concrete, the other one made out of wood, subject here to an earthquake. And you see here the complete pancaking, and here a partial one here. It was a very severe earthquake, which we considered here. So the approach can do all type of loads here for the system. Now, let me say that what happens when actually a structure fails? Let me bring it back to the question of why current tools are not sufficient to do this here. Let me go back once again to kinetic theory of gases, so the relation between the pressure, the temperature, and the kinetic energy. In fact, if you apply such a definition, which works perfectly for gas, that's the temperature you measure actually in your home right now with the thermostat. If you apply the same definition for structures, you can actually define something like the kinetic temperature of structures, where you see that this temperature, which is by analogy to gases, is the kinetic energy of the structure divided by the number of degrees of freedom, which we know of the structure, the Boltzmann number. This is just a constant number, and then the dimension here. But the most important thing is that it captures here the mean square speed fluctuations. So a structure which is in complete static conditions has a temperature, kinetic temperature, which is zero. Nothing moves in the system. But when it is subjected, as it is here in this here, for instance, to a buckling, what you see then on the side is this burst of the kinetic temperature when it buckles, and then it slows down because the structure doesn't break. But actually these curves are extremely important, because what they show also is that the structure does not return to the temperature, to the reference state where nothing moves. In fact, this is known as the zeroth law of thermodynamics. Two systems are in equilibrium if they have the same temperature. The fact that buckling occurs means it's an out of equilibrium phenomenon. We all know that here, but the theory can capture that here. The model can do that here with high accuracy. And then you can imagine that actually these maps here of a town here are basically maps of the kinetic temperature, the maximum kinetic temperature a structure has been subject to during an extreme event. And by doing so, we condense this fluctuation information induced by the external pressure onto the structure through the breakage of windows, through the breakage of, through the damage of roofs, all the way to the structures here, into such temperature maps of the system. So the second lesson learned here is that structure's fragility actually relates intimately to bond breakage. And that must be the focus of the tools that want to be quantitative at the scale of structures. So classical tools can capture this bond breakage. For instance, classical yield design models, plastic hinges, etc., fail to capture these type of things because they have a controlled level of dissipation. They stay in the continuum realm. What we can do with this MD-inspired approach is actually to model both structural elements, which are strong bonds, and non-structural elements, which are weak bonds, as long as we can quantify this strength of the bondage between mass bonds. The solution, thus, in order to be quantitative at the scale of structures here, is to incorporate bond breakage into the fragility curve assessment. Which brings me to the fragility curves, the last point I would like to address here. Fragility curves expresses the likelihood of damage, actually. The broken links for a given load, or more specifically, the probability of broken links for a given load. Now, in an ideal world, we would see enough structures failing, same structures failing, so that we could develop for each structure such a fragility curve, the likelihood of damage to occur. Of course, this, first of all, we don't want that, to see so many structures fall, breaking. Second, the approach which I just presented is just apt in order to simulate just this year for the determination of fragility curves. This is in contrast to the current toolbox that exists for these type of studies, which is HAZES, which cannot take on a case-by-case basis. Similar buildings show different responses, different construction, have different uncertainty for better or for worse. So it is not specific enough in order to address the diversity of the building stock in a city and its fragility, the likelihood of failure when subject to such extreme events. So the approach which we here take basically is like a thought experiment. It's like a radiation approach. So imagine you have an outside source and you have some structural elements, and this is a molecular structure, but it could be a beam as well, or some springs here between masses. So if you would like to know what is the likelihood that one bond breaks compared to another one, well, all what you need to do is in essence, and let me show you this again here, you take out a bond, you evaluate the change of this energy, and see whether this is the maximum amount of energy a structure releases. So that's behind this bond rupture radiation approach, which is a molecular approach used for many applications. For instance, the gas shale revolution, which is ongoing, is just based on this type of theories in order to understand whether or not one can recover shale gas from the organic rich shales in different places. So that's basically the fundamental idea here, that we probe all bonds. And what we then obtain is basically the number of bonds. So N here, you see here, initially we have here 1,600 bonds. And then as the load here, in that case, we call it mu, this load here, is changed here, we see this reduction of broken bonds. The slope of this curve, by the way, is in essence the rigidity of the structure, and here the structure is completely wasted. So how to determine from this type of information of this radiation-inspired approach fragility curves? Well, the first thing is actually to calculate here damage energy, so the energy associated here with the breakage of those bonds, interpolate damage in between, and define damage states in terms of broken bonds, then the percentage of broken bonds you're interested in. And by doing so, we then obtain here the probability of exceeding a certain damage state here in functions of a load. So given a certain load here, you have a certain probability of exceeding a damage state here, meaning a number of broken bonds. Just in this example here, if you take a 7-story building here, loading with uplift here, just as a case study here, well, you can obtain then here a building level fragility curves for different type of materials. So materials actually here matters here. So given a certain load, let's say here 0.2 here, you see that here the different damage levels here is the probability of exceeding at this level here the damage state here would be 15%, let's say. Well, when you have this second structure, you have the same amount here, it would be 60%. So that means that you can incorporate then into the design of structures these fragility curves with regard to the probability of failure. And again, these are related to fluctuations of the bond breakage that occurs given a certain load to which the structures are subjected. In other words, fragility deals with the probability of broken bonds, and design codes built upon mean field models naturally fail to capture this fragility that results from those fluctuations because we have mean field theories and do not capture the fluctuations actually that occurs here. So solution here of the approach which we have developed is basically to incorporate these structural material fine-tailored fragility curves into the resilience assessment of structures. Let me wrap up this here to say what's next here. My motivation here is clear that I want you to join us with your community to make your community more resilient for extreme events, be this hurricane, earthquakes, we're working right now on fire, on flooding, and so on, so that this becomes part of the design practice for engineers. If you want to know for a given system, what is the resilience of your community? The approach is in place, which starts here with the city texture, which just requires access here to a computer and this free database of the building stock to incorporate here uncertainty in the hazard occurrence inside into the approach. As you zoom into this building here, then you add the building's bond response to structural response uncertainty. And you may ask yourself, oh, will that take a PhD thesis in order to calculate the response of one building? No, it will not. In fact, all those responses of specific buildings are made available through a library, actually, for different building types through our work. Finally, if you would like to know what is the fragility curves in order to assess what amount of elements have been broken in your system in a building, whether these are non-structural or structural members, the approach which we developed permits just that here for an urban resilience assessment. However, that would be the assessment. In the end, we need to design to become more resilient. So this actually requires to go the inverse route. Starting with the fragility curves, include materials into the resilient design, which right now is not part of the overall picture. this is an absolute critical step here where we can take decisions at a local scale of our buildings. We can then integrate this here, include this structural response into structural resilience, considering that here in the architectural design, in the design of a specific structure made of a certain material, this response, this number of possible bonds and the cost to repair them with regard to a given hazard. And finally, incorporate this information into city texture as each city requires certain materials and structures. So inversing this approach actually permits, as we believe, to enhance the urban resilience for all relevant hazards. With this, I would like to close. I hope I was able to show you that resilience can be done, and it must be done. Thank you very much.
Thanks so much, Franz. You've given us a lot to chew on here, and hopefully we have some good discussion. As I mentioned, if you have questions, please type them into the question and answer box in the lower right of the WebEx portal there. The first question we had is a simple one to answer, and it's that, is this being recorded and can I share it? And the answer is yes and yes. If you're on our mailing list for these webinars, then we'll be sending out a link in a day or two that has the recording on YouTube that you'll be able to share. If not, then you can check back on our website, and we have a portion for webinars where we'll be able to have all those. So in the meantime, while people are writing in their questions, it looks like maybe we got one more that I can go to first. Here's the first question we have. I didn't quite catch the idea of recovery time at the building scale. How do you factor for that in building resilience?
Mm-hmm. So in order to, it's a very good question, and actually it brings together the prediction of bond failure, number of bonds broken, together with the bill of activities. So the current approach is actually, if I know what is the probability of failure of certain elements, I can convolute this here with the availability of services, for instance, to repair windows. There's the supply-demand models typically behind here, which permit to calculate then the time it takes, not only for one single building, but actually for damage within a community, a large enough community, to respond for time to repair. So this basically is the approach which I showed you, provides the demand side. It needs to be brought together with the supply side, which of course is regional specific, so city specific. But just keep in mind, if it's only one building that fails, well, you just go on the open market, and the demand can immediately met by the supply. However, if there's large enough damage of let's say all windows here, you can be sure that the process per se will be delayed. So it is actually the combination of demand and supply here. What we provide here is the demand, connecting it to the supply.
That's great. Thank you. We have a question about, can you explain the fragility curve further? What do the different colors represent? So I think that's in reference to some of the work you presented on the law. Yeah.
Okay. Well, let me show it. Let me show this maybe here. What do they respond? I have a certain load, and by the way, this load comes, as we saw before, with a certain probability of occurrence. So for which we saw before, depending on the texture. But let's assume you have a certain value here. Then you have a probability of exceeding a damaged state. So let's say you're allowed to have a 10% damaged state of your building, meaning you have to replace, in this case, actually here, this type of, so 10% you allow here. How to read this curve then? It means that at a load of 0.075, you may have a 3% of damage. If you go a little bit further, that means here still 10%. You permit at 10%, the load, corresponding load would be here, let's say 0.1, right? As you go further here, it would be here 0.125, so that would be now 10%. Would be 10% of broken bonds here, and if you go here with the 10%, it would be the corresponding load level would be 0.16 or 0.17 here around it. So that's a way of reading. If you say, let's say, I don't want that there is a higher damage state, the probability of damage state than probability of 10%. Now, engineers typically work with 5% fractile or 95% fractile, which basically means you would put yourself here at the 5% level here, and would say, I don't want that more damage occurs with this here, which means that actually the significant damage, a maximum low for the structure here, would be here at this load level. If you compare this with another fragility down here, 5%, you would see it would be a very extremely small value of a load applied to the system. So the way of reading these curves is you either prescribe a probability of exceeding a certain damage state, or you go into these curves with a certain load and get out the different probability of damage for on the top, the non-structural elements. No, on the bottom, the non-structural elements and the structural elements given a certain load of the system.
Thanks. That's helpful. I had a question if you could elaborate a bit more on the texture. It's really striking how much that texture really affects the pressure distributions that different cities face. But obviously, there's not much we can do about the orientation of buildings in existing cities. So how can we use that information to help us still support resilient design? Acknowledging we're not going to be able to change the orientation of buildings, nor can we always have that much say when kind of new neighborhoods are created.
Yeah, so I think this is you're absolutely right. We will not rebuild our cities fundamentally. We don't want to erase them first and redo them, so absolutely right. But I think this multi-scale approach shows nicely, let's say, how to go about this here. That means if we want to reinforce, we basically want to reinforce these fragility curves of the materials through material choices in the system in order to see, given that we don't want to change the texture here, that we enhance, in essence, the resilience of the entire community by reinforcing at the building scale. So these three elements are not independent of each other. If we're not able to change anything at the building scale, at the city scale, well, then we need to go to the component level and reinforce them. So the multi-scale approach shows it nicely that there's a propagation actually from the material to the type of structures to this level. By the way, this is already done in some fields. If you take earthquakes in California, for instance, it was precisely this fragility curve approach, which was that we need to retrofit structures in order to obtain a higher resilience or a damage of this point. What generally is not taken into account in earthquakes is the interaction between buildings. Something which we haven't studied, so I cannot say what would be the impact of several buildings at city texture scale. I know, however, that for instance, from Mexico City, that because of the very soft soil which is there, the interaction between buildings actually should be pretty high. While when you have very rigid soil, which is sort of here on the here in Middle America, Middle U.S. Toward the coast here, the interaction should be less. So there should be actually also city scale interactions. But the way of doing this here is classically starting here at the material scale, incorporating into the structures and carrying it on all the way to the city in order to see, did we obtain with this here a higher resilience? Resilience being defined here as the number, the time it takes to bring the city community back to the same or higher level of performance after an extreme event.
And sorry, there's one follow-up question on the fragility curve. It says in the legend, what is NB and what is NO, or N naught, I think is what it is.
So N naught is the initial number of bonds, and so this is basically broken bonds over initial number of bonds, right? So this is here. This was the case study of such a simple structure here. But you readily understand that I can do this with much more complicated structures here, separating structural elements from non-structural elements. The direct output actually of the simulations are the broken bonds. So we count them actually, the broken bonds and the variability, which is the key of it. So it's the fluctuations actually of those broken bonds, that there's not only one single response of a system, but there's a variety of systems mimicking actually the fact that I had a large amount of tests carried out on the same structure. That is the strength of this it's called Grand Canonical Monte Carlo approach, which we employ for assessment of fragility curves of structures.
Great. I think so. As a closing question, a lot of times when it comes to resilience, the solution that a lot of people want to propose after a disaster is to change building codes. And while that's certainly a laudable goal, that it can be kind of a time-consuming process that can have sort of variable results. So how do you think that the approaches, this multi-scale approach that you've discussed, could sort of enable more maybe like a cultural change or just some other ideas about building that maybe wouldn't rely just entirely on building codes?
So I'm always careful when it comes to cultural changes, to be honest. So I need to work with the existing culture. So first of all, I think that the wind maps that exist, at least what I have seen for all the case studies which we did, the wind speeds which were on these maps looked exactly what the structure was subject to. Now, it doesn't only happen all 100 years or 500 years. It happens much more often. So that's another point of view. But the order of magnitude of the velocity is correct. So what it takes then actually is a local intervention, meaning city managers here, when it comes down to designing buildings, could make use of this information of city texture in order to update the pressures. Design pressures to which for which buildings are designed. They are specific to the location, and they can be easily made available for at the scale of city managers. This is not you don't need a mayor to run computational fluid dynamic simulations. This is simple equations will be done once and forever, and it's and will be updated as the building stock evolves in a city. So this can be done relatively easy online without going any way further of changing design codes. You don't need to change the design codes for it. What you need to do is basically a local prescription of magnifying these values. That would be the first one here. Another point about this here is really how do you go about here to connect here with other things. So my first point was this mapping online, large public, federal, state, city scale. A second one is the engineering community. I'm well aware that I, as a structural engineer, wasn't educated with these molecular-based methods. So what we need to bring them into is what is called streamlined resilience for the engineering and building community, which is what we tried of doing by running these simulations for type of structures like the DOE structures, etc. And only in the case of exceptional structures would we rerun those type of simulations. So this streamlined streamlined resiliency, which is at the building scale, is currently underway here, so that we make this available for the community. In fact, for a number of buildings, it's already available. Finally, it comes down in the end to combine the tools which are available. So whether these are mapping, these map solutions, the streamlined engineering community, together with some pressure at an institutional community scale. And there are different organizations who aim at enhancing resilience. One is the U.S. Resiliency Council, which provides institutional rating for communities in terms of resilience. So there are organizations out there actually who do just this here. So the tools which are available now, or which are presented here, we always have in mind here behind the large public and the engineering, but it requires this institutional rating system, I think, to feed this into the public consciousness, and not only the day after a storm or the evening after a storm, and forgotten then 2-3 days later.
Great. All right. Well, I think that's a perfect way to finish. Franz, thanks so much for taking the time to share with us the work that your team is doing. It's given us a lot to think about and hopefully spurred some additional conversations. If you want to follow up, please go to our website, cshub.mit.edu, where we have a lot of information on this and also have some other ways to get in touch with us. So we look forward to seeing you in July for our next public webinar, and details will be sent out about that. Thanks so much, and enjoy the rest of your day.